A fully loaded supertanker weighs more than 500,000 tons. Every kilogram of that is steel, machinery, cargo, and fuel, not a gram of wood, not a fiber of anything that floats by nature. Drop a single steel plate off the side of that same ship, and it goes straight to the bottom, and does not stop until it hits the seabed. That is not a contradiction. It is the clearest possible demonstration of the one physical rule that makes global shipping possible, and understanding that rule along with how fragile its application turns out to be changes the way you look at every vessel that crosses deep water. The question most people carry in the back of their minds is simple: steel sinks. So, why doesn't the ship? The honest answer involves geometry, displaced mass, and a margin that naval engineers track obsessively from the moment a ship is loaded to the moment it reaches port. That margin has failed before. When it does, the consequences arrive in under 60 seconds. Today you will understand exactly how that rule works, why it has a breaking point that engineers calculate before every single voyage, and what happens to a vessel and the people aboard it when the calculation stops being right. A fully loaded supertanker weighs more than 500,000 tons. Every kilogram of that is steel, machinery, cargo, and fuel, not a gram of wood, not a fiber of anything that floats by nature. Drop a single steel plate off the side of that same ship, and it goes straight to the bottom. That is not a contradiction. It is the clearest possible demonstration of the one physical rule that makes global shipping possible, and understanding it along with how fragile its application turns out to be changes the way you look at every vessel that crosses deep water. Start with the numbers. The Knock Nevis, the largest ship ever built, had a fully loaded displacement of 657,000 metric tons. Its hull was formed from continuous steel plate, 20 to 30 millimeters thick, depending on location. Steel has a density of 7.85 grams per cubic centimeter. The North Atlantic seawater beneath it has a density of 1.025 grams per cubic centimeter. That is a ratio of nearly 8 to 1. Steel is almost 8 times heavier than the water it must sit on. A solid steel cube, 1 meter on each side, weighs 7,850 kilograms. 8 tons. Drop it into the ocean and it sinks at several meters per second without slowing. A steel sphere the size of a tennis ball hits the bottom of a pool in under 2 seconds. There is nothing in the material itself that creates buoyancy. The composition offers nothing useful on that front. The Knock Nevis was 458 meters long and 68 meters wide, with a fully loaded draft of 24.6 meters. From the base of its keel to the top of its mast, it stood taller than a 30-story building. It floated reliably for 29 years, crossing ocean after ocean carrying crude oil. The material is not the answer. The shape is. When a ship's hull enters the water, it does not sit on top of the surface. It pushes water out of the way it displaces a volume of water equivalent to the submerged form of the hull. That displaced water has mass, and seawater, obeying a principle Archimedes worked out around 250 BC, pushes back upward against every square centimeter of submerged surface with a force exactly equal to the weight of the water displaced. That upward force, is buoyancy. A ship floats when it displaces a weight of water equal to its own total weight. The hull sinks into the water until it reaches that equilibrium, and there it stays. The reason this works for a steel ship, but not for a solid steel bar, comes down to one thing. The ship is not solid. It is an enclosed volume of air and structure. The hollow hull, the cargo holds, the ballast tanks, the machinery spaces, the passageways, all of it creates a structure whose average density, calculated across every cubic meter of its total volume, sits well below 1.25. Not because the steel became lighter, because the steel surrounds an enormous amount of nothing. The depth to which the hull sits is called the draft. Load the ship with another 100,000 tons of cargo, and the draft increases. Pump out the ballast tanks, and it decreases. Every commercial vessel carries a set of horizontal load line marks on its hull, painted clearly on the steel amidships, that show precisely where the waterline should and should not fall under different loading conditions. These are called Plimsoll lines, after Samuel Plimsoll, a British merchant and member of Parliament who spent the 1860s and 1870s campaigning for their introduction. Plimsoll's campaign began after he observed a pattern that ship owners preferred not to discuss. Vessels were being loaded well past any reasonable limit, sailed with minimal reserve buoyancy, and when they sank, which they did, regularly, in numbers that would be considered catastrophic today, the owners collected insurance and moved on. The sailors did not. Ships so overloaded that their crews knew they were sailing to their deaths were called coffin ships. Parliament passed the Merchant Shipping Act of 1876, making load lines mandatory on British-flagged vessels. Before that, there was no legal standard. You could load a ship until the deck was nearly awash and call it ready to sail. Look at the thumbnail for this video. The hard line between the red-painted underwater section and the dark steel topside is the current water line. The red is antifouling paint, a specialized coating that prevents barnacles and marine fouling organisms from colonizing the hull and adding drag and weight over a long voyage. But the boundary also records how much reserve buoyancy the ship retains. Every centimeter that red section drops toward the waterline is a centimeter less between the main deck and the sea. Below the waterline at the bow, there is a rounded underwater bulge. That is the bulbous bow, visible clearly in the thumbnail. It looks like deadweight. It is not. The bulb projects ahead of the hull and disrupts the bow wave the vessel generates as it moves through the water. A ship underway creates a wave system, a bow wave and a stern wave, and the energy that goes into generating those waves is energy not going into forward motion. The bulb cancels part of the bow wave by creating a second, smaller wave that interferes destructively with the first. The net effect on a large tanker or bulk carrier is a fuel saving of 10 to 15% per voyage. At 100 to 150 metric tons of bunker fuel burned per day on a large vessel, that matters. Buoyancy is half the story. The other half is stability, and this is where most explanations stop, which is exactly the wrong place to stop. A ship can have perfect buoyancy and still roll over. These are separate problems. Stability is governed by the relationship between two calculated points inside the hull, The first is the center of gravity, the average position of all the ship's weight from the keel to the top of the funnel. The second is the metacenter, a geometric point derived from the hull's shape and the way the center of buoyancy shifts when the ship heels. When a ship heels sideways, the center of buoyancy moves toward the lower side because more hull is now submerged on that side. If the metacenter sits above the center of gravity, that shift creates a righting moment, a force that pushes the ship back upright. Positive stability. The ship heels, the geometry responds, and the vessel rights itself. If the center of gravity rises above the metacenter because cargo is stacked too high or ballast tanks have been pumped empty without adjusting the load distribution, or a modification has raised the ship's center of mass beyond what the design assumed, the righting moment reverses. Heeling now pulls the ship further over instead of pushing it back. At that point, the outcome is not a gradual list that gives everyone time to respond. It is capsize. Naval architects calculate metacentric height before a design reaches a shipyard. They calculate it again during construction, during sea trials, and every time a loading plan is finalized before a voyage. Metacentric height is not a fixed property of the ship. It changes with every ton of cargo loaded, every tank pumped out or filled, every ton of fuel burned across an ocean passage. The ideal value balances two competing concerns. High metacentric height makes a ship stiff. It rights itself quickly and decisively after a roll. But it also rolls sharply and frequently, stressing the hull structure and making life aboard difficult over a long passage. Lower metacentric height, still positive, produces a slower, gentler roll that is easier on the structure and the crew, but with a narrower margin before the system tips into negative territory. The people who manage this are not working in theory. They are doing applied physics in real time on a moving platform across thousands of miles of open ocean. The idea that iron was unsuitable for boat construction persisted well into the 19th century. Wood floated. Iron did not. This was not an engineering conclusion. It was a widely held certainty, and it was wrong, but it shaped the industry for decades. The first practical iron-hulled vessel was a flat-bottomed river barge built by the English ironmaster John Wilkinson in 1787. Wilkinson made his living manufacturing iron and had a commercial motivation to demonstrate that the material was more useful than the conventional wisdom allowed. He launched his barge, which he named Trial, a word that says something about expectations, on the River Severn. It floated without incident. The shipping industry's response was largely indifference. In 1822, the first iron-hulled ocean-going steamship completed a crossing. The Arran Manby was built in sections at the Horsley Iron Works in Staffordshire, assembled at a London dock, and sailed from there to Paris under her own power. She crossed the English Channel and proceeded up the Seine, a voyage that would have been unremarkable in a wooden vessel, but which attracted sustained skepticism when the hull was iron. She made it. The calculations had been correct. The skeptics noted the result and mostly did not change their position. What moved the industry over the following half-century was not persuasion, but arithmetic. Iron hulls did not rot. They were not eaten by the teredo worm, a wood-boring mollusk responsible for ending the useful lives of countless wooden vessels in warm waters. They could be built larger than any structural timber could provide. The demand for wood of the sizes needed for a large ship had exceeded what forests could reliably supply. and they lasted. A well-maintained iron hull had a service life 3 to 4 times that of equivalent wooden construction. When steel became cheap enough to use its shipbuilding scale in the 1880s, stronger and lighter than iron both at once, the transition accelerated. By 1900, wooden deepwater commercial vessels were curiosities. By 1910, they were museum pieces. The principle throughout was identical to what Wilkinson had trusted in 1787: displacement, density, equilibrium. The material changed. The physics did not. On the night of March 6, 1987, the cross-channel roll-on roll-off ferry, herald of free enterprise, sailed from the Belgian port of Zeebrugge with its bow doors open. The assistant boatswain, whose responsibility it was to close them, had fallen asleep in his cabin between loading and departure. The officer on watch never checked. There was no indicator light on the bridge, no instrument, no readout, no warning to show whether the doors were shut or open. The ferry sailed with the bow open to the sea. 90 seconds after clearing the harbor entrance, water entered through the open doors and reached the car deck. On a roll-on, roll-off vessel, the car deck is a single, undivided, open space running the full length of the ship from bow to stern. It must be. Vehicles drive in from one end and out the other, which means there are no watertight bulkheads, no internal compartments, no barriers that can slow the spread of water across the full length of the deck. The flooding was total and immediate. The ship heeled hard to port, crossed the limit of positive stability, and rolled onto its side in under 60 seconds. 193 people died. The water was 18 meters deep. The sea state was ordinary. There was no storm, no exceptional condition. The buoyancy mechanism failed because it depended on watertight integrity that a single open door had destroyed. The disaster rewrote international shipping safety regulations. Damage stability requirements, specifying how much flooding a ship must survive while maintaining positive stability, were tightened substantially. Large passenger vessels now must survive simultaneous flooding of 2 adjacent compartments. Door position indicators are mandatory. Departure checklists require positive confirmation of every watertight boundary before leaving port. 7 years later, in South Korea, the ferry seawall capsized because an illegal post-construction modification had raised the ship's center of gravity beyond what the original stability calculations assumed. Cargo shifts during the initial list accelerated the capsize. 304 people died, most of them high school students on a school trip. In that case, the paperwork existed, the loading plan existed, the stability certificate existed, the underlying numbers had changed because someone had altered the ship without recalculating the consequences. The physics does not negotiate. Either the righting moment exists at the critical angle, or it does not. Paperwork does not change the geometry. On every commercial vessel, one officer carries specific responsibility for the loading plan. On a tanker, this is typically the chief officer. Before cargo operations begin, they run the full stability calculation through dedicated software, NAPA, MaxSurf, or an equivalent system. Every tank aboard is entered. Ballast tanks at their current fill level, fuel tanks, cargo holds, fresh water tanks. The calculation produces a trim and stability report showing the expected draft at bow and stern, the metacentric height at departure and estimated arrival, the ship's stability curve across the full range of heel angles, and the maximum weight permitted in each cargo hold. The report is signed by the chief officer, filed aboard, and submitted to the port authority before departure. At sea, the calculation is run continuously. A large VLCC burns 100 to 180 metric tons of fuel per day. As fuel is consumed from different tanks in sequence, the center of gravity shifts. Ballast tanks are adjusted in response to keep the ship's trim and stability within the parameters set in the loading plan. On a long Pacific or Atlantic passage, the chief officer may adjust ballast distribution 2 or 3 times in a 24-hour period, responding to changes in loading as fuel is consumed and sea conditions change. An empty ship running in ballast without cargo is often more technically demanding than a loaded one. The hull rides high. The propeller may approach the surface, losing thrust and causing vibration. The natural rolling period of the hull shortens, and if it happens to align with the period of the prevailing swell, resonance can develop. The ship begins rolling more deeply with each cycle, the rolls reinforcing each other faster than any course correction can damp them out. Modern ballast systems carry tens of thousands of tons of seawater aboard, specifically to push the empty hull deep enough to avoid this condition. An empty VLCC routinely carries 80,000 to 100,000 tons of seawater in its ballast tanks, not because the ship needs ballast to float, but because it needs the hull submerged deeply enough to keep the propeller and rudder effective and the rolling period away from dangerous resonance. This work is invisible to everyone except the crew. The cargo receivers at the destination port see the ship arrive and the cargo come off. The trim calculations, the ballast log, the metacentric height at departure, all of it is filed, signed, and archived. None of it appears on the manifest. The next development in hull design is not coming from steel, it is coming from air. Several shipping companies and engineering firms have been trialing systems that force millions of tiny bubbles under the flat bottom of a ship's hull during transit. The bubbles form a compressible film between the steel and the water, reducing the skin friction that accounts for a significant portion of a ship's total resistance at cruising speed. On a large bulk carrier, the reduction in fuel consumption runs from 5 to 10% per voyage. Silverstream Technologies, which has systems in commercial operation on vessels crossing the Pacific, reports average savings around 8% on fitted ships. The system does not alter the displacement. The ship floats at the same draft, displaces the same weight of water. What changes is the energy required to move through the water. Hull form research has moved into biology. The humpback whale's skin is covered in small rounded tubercles, bumps along the leading edge of each pectoral fin, and these tubercles have been shown in tank testing to reduce drag at the angles of water flow common in slow-moving ships. Several research programs are prototyping hull coatings that replicate the texture. Projected savings are modest, 3 to 5%, but at the scale of global shipping, tens of thousands of vessels, each burning thousands of tons of fuel per voyage, modest percentages become very large numbers in aggregate. None of this touches what John Wilkinson understood in 1787, watching a barge made of iron sit quietly on the River Severn. The principle he trusted is old. Old as a bathtub in ancient Syracuse, old as the first reed boat anyone pushed out onto the Nile. What makes a steel ship float is not the steel. It is the precise management of the volume the steel encloses, the weight distributed within that volume, and the geometry that keeps the whole structure pulling back upright whenever the ocean attempts to tip it over. The ocean attempts this constantly, in every sea condition, on every voyage, at every moment the hull is in the water. The stability calculation is the answer that holds. When it stops holding, when one number in that chain is wrong, what follows does not announce itself in advance. That is the kind of explanation this channel provides, the real mechanism behind things that seem simple until you look at them squarely. If that is what brought you here, there is more where this came from.